So there's a way to start with a group action on a finite set and upgrade it to something called a permutation representation. So here's the procedure. I'll start with my action and I'll pick a vector space whose dimension is equal to the size of the original set. I'm assuming it's finite. I'll pick a basis of that vector space. And then I'll choose a bijection between that basis and the set. So if I have an element little x in the set, I'll call the corresponding basis element ux. So a typical element in V looks like a sum of some scalars times these basis elements. That's a typical element in V. I will use sometimes the notation Cx for this particular vector space. Okay, given this vector space, we can now define a representation rho from G to the general linear group of this vector space. And I'll do it by saying what it does on basis elements. Rho sub G applied to the basis element ux is defined to be ugx, where the gx is the action. So remember, if I have an element of the set, element of the group, I get a gx, also in the set. So this defines a representation, and that's what's called the permutation representation. We've seen this sort of thing. For instance, I could take the symmetric group, and I could take rho to be the standard representation. Well, that's an example of a permutation representation. I'm starting with the action by the symmetric group on the set of elements 1 through n. That corresponds to the standard basis inside C to the n. And this formula gives me the formula for the standard representation. But in fact, I can do this for any G set. Now, the nice thing is that permutation representations have very computable characters. Let's say G acts on a set X, and I'll let rho be the corresponding permutation representation. Then the character of the permutation representation has the following formula. Its value at a group element G is actually an integer. It's in fact the order of the fixed set of G. And so to remember, fixed G is by definition the set of elements in X such that Gx equals X. Why is this? Well, if I take rho G and I'll write it in terms of the basis, let's write ux1 up to uxd corresponding to the elements of the set X. So let's call that matrix A. Well, that is a permutation matrix. That is, it's a matrix which in each column has exactly one entry, which is 1, and all the other entries are 0. Furthermore, what are the diagonal entries? Well, the diagonal entry AII, it's either 1 or 0. It's 1 if GXI is XI, and it's 0 if GXI is not XI. And so, of course, that gives you the formula for the trace of A. It's exactly the number of XIs that are fixed by G. So that's a convenient source of representations whose character you can compute easily. There's a very important example called the regular representation. This is produced from the left regular action. G acts on itself by left multiplication. And so we get a corresponding representation, which I'll call L, and is the regular representation. So L stands for left. The dimension of this representation is exactly the order of the group. The representation is given by the formula LG of the basis element UX. Here both G and X are elements of the group. It's just UGX. Well, we have an easy formula for the character, so let's compute it. The character of the regular representation at element G, well, there's two cases. If G is the identity, then left multiplication by G fixes every element of the group. So that's actually the identity matrix. So its trace is just the dimension, which is the order of G. And if G is not the identity, then it fixes no element of the group under left multiplication. So the character there is 0. That's the character of the regular representation. Okay, so here's the great fact, which we're going to prove. Every irreducible representation is contained in the regular representation. If you want to find every irreducible, just look for sub-representations of the regular representation. Here's a precise statement. So as usual, I'll write lambda 1 up through lambda s for the complete list of pairwise inequivalent irreducibles. Irreps is an abbreviation for irreducible representation. I'm going to write d sub k for the dimension of lambda k. Then we have the following decomposition of the regular representation. It's equivalent to d1 lambda 1 direct sum ... up to ds lambda s. The multiplicities of the irreducibles in the regular representation are equal to their dimensions. That's a great fact because dimensions of irreducibles are always positive. The 0 representation is not irreducible. So that tells us that every irreducible can be found in L. We also get another statement. The order of the group turns out to be equal to the sums of the squares of these DKs. So that's a new relationship involving the dimensions of all the irreducible representations and relating them to the order of G. How do we prove this? Well, we just use characters. So I'm going to write chi k for the irreducible character chi lambda k, just to make it easier. Let's just compute the inner product of the character of the regular representation with the irreducible characters. Remember, this number is going to be the multiplicity of that irreducible in the regular representation. But we have a formula for the inner product. Now, we also have a formula for the character of L. In fact, it pretty much always vanishes except on the identity element. So we only get one term coming from the identity element. We also know what the value is on the identity element. It's the dimension of the representation, which is the order of G. And we also know that the value of the other character on the identity element is its dimension, the dimension of that representation. So that works out to dk. dk is a real number, of course. And that's our formula. That's the multiplicity. For the final statement, what I'll do is I'll take the character of the regular representation, which we now know had better be a sum of the irreducible characters with the given multiplicities that we just showed are dk. And what we'll do is we'll evaluate these functions at the identity element. So on the one hand, I'll have the regular representation at the identity. That's the dimension of the space. That's the order of the group. But that's equal to the sum of the evaluations of the irreducible characters. But each irreducible character at identity is just the dimension of its representation. That's also dk. So that's dk squared. That's that formula.